so I will continue where I left off yesterday. And I think I made it maybe 2/3 through my lecture yesterday, so this is more or less the last third of my lecture, first lecture. But yeah, so yesterday we talked about hold on. We talked about sorry, I'm not sure if I'm getting it right. All right, so yesterday we talked about partial amplitudes. So essentially we can label them as some permutation. In general, we can do any permutation, but then we said that you only need to consider a small subset of them because of the Kleist-Coif relations. It's not working? It's a bit strange. All right, can you hear me? It's a bit lower.
Yeah, I lowered it because
yeah. Oh, it's too loud. Okay, thanks. So you can pick some fix two of the legs. You can fix one, and then you can have some. Let's call it just sigma here and n. So you fix two of them, and then you have some generic n-2 permutations. So this belongs to S n-2. And yeah, the relation I showed you last time, I'm not going to quote them again here. But what's interesting is that these relations are actually not very mysterious if you think about just what kind of diagrams enters into these partial amplitudes. So you can actually make the KK relations manifest by just writing out the diagrams that contribute to the amplitude. So let's do that. So let's consider our partial amplitude 1 sigma n, and it's going to be a sum over planar graphs. As I said, it's a planar amplitude essentially. And I'm also going to restrict to cubic graphs because it turns out that that's fully sufficient for describing what I need to describe. So planar cubic graphs. And I'm just going to call the graph label I generically. So we know that typically Feynman diagrams or graphs, they have some numerator, which I'm going to call Ni. They have some denominator, which I'm going to call Di. And I'm also going to put in some potential sign that could be here. So let me just do it a bit sketchy and call it some sign that depends on the permutation sigma here. And I'm not going to exactly say how it depends on because, well, I don't have a great way of writing out the dependence, but it has something to do with, you know, permuting two legs. You might introduce a minus sign or not. And I'm going to give you some examples, so don't worry about it. But essentially, we can write our diagrams like this. This just captures the poles of your Feynman propagators. Yeah, so this is just the poles of Feynman propagators. And this is my kinematic numerator. And so I call it kinematic because it does only depend on kinematic variables and not color variables. All right, and let me also try to say what the range of this sum runs over. So as I said yesterday, if you consider all cubic graphs, then, yeah, so this is just a recap from yesterday. Essentially, you have a range of I going from 1 up to 2n minus 5 double factorial. Now, if you just restrict to the planar cubic graphs in some canonical ordering, for example, 1, 2, 3, and so on, that's the canonical ordering. So do all. Well, so do planar graphs. And obviously the labels here might not correspond one-to-one up there, but let me anyhow call it I again. So the number of planar graphs is actually a well-known number. It's the Catalan number, Cn minus 2. So the Catalan number Ck is simply 1 over k plus 1, and then 2k choose k. That's the Catalan number. And I'm not going to derive it, but that's the number of planar graphs. All right. And then, what is this minus 1 to the permutation? Well, to raise to the permutation, what does that mean? It just denotes here a permutation sign, a permutation dependent sign. And so the property that this sign has here is that if you have a numerator, and let me try to do it graphically here. So a numerator of this particular graph here, 1, 2, 3, then if you permute the order of any two particles, you should get a minus sign. So the numerator of this graph is the minus the numerator of some crossed graph. And it's just designed to mimic the same behavior for the color factor. So if you have a color factor for the same graph, so this notation I just mean that you have a graph and it has a color factor. And what you want is that the color factor has an antisymmetry when you flip two legs. And so the numerator is just designed to have the property that it has the same antisymmetry under flipping of legs. And here I was a bit sloppy and I just put the sign up front because typically what we do is we just pick some canonical, we pick some arbitrary labeling of our numerators, and then depending on which particular permutation sigma we consider here, we might have to put in a minus sign or not. Right, so we will see that in some examples. It doesn't recognize my face, I guess, when I have that. All right, there we go. All right, so the claim here, when you write your amplitude like this, the KK relations are just going to be manifest because of this sign here. Essentially, all the KK relations are going to be pairwise cancellations of diagrams depending on what sign you have here. So let me write out the claim. So the KK relations manifest. Also, because I'm summing over all planar graphs, it's going to be obvious that I have planarity and cyclicity. Also, since I wrote out the poles, which obviously you have to write out in more detail in this specific example, but essentially the poles are also manifest. and also reversal. And U1 decoupling. And as I said, U1 decoupling is just a subset of the KK relations. And this is just a claim, and in order to justify the claim, let me just give you an example. So let's consider a 4-point example. So we have 1, 2, 3, 4 ordering, and so I can write that as a sum of diagram. So let's say that's an S channel. Let me also draw the diagram such that it's clear. Maybe I can draw a slightly bigger. This is my S channel. So this is sitting on top of 1 over S. And then it's convenient to put in a minus sign here. And it has to do with that, just flipping legs, you can get a minus sign. So let me put a minus sign there. And then so I have a T channel corresponding to this graph here. T. And there's only 2 graphs here. So that is the, you can get that from the Catalan numbers. 2 graphs. It's obviously cyclically symmetric. There's maybe a minus sign there, but that's, it has to do with this permutation sign here. So maybe I should have, I could have put a plus sign there, which would make it much more obvious that it's permutation symmetric. But for later purposes, I'm going to be more comfortable with a minus sign, so let me keep it there. So what I actually want to demonstrate here is that the phase-coef relation, which is the same as the U1 decoupling identity, is going to hold. So let me write down the 2 other permutations that I can write down at 4-point. So this permutation here, sorry, I have 2 3s there. One of them should be a 2. So it still has an S channel because leg 3 and leg 4 are next to each other. So there should still be an S channel. But you can work out that the sign has to be negative. And the reason for that is essentially I use cyclic symmetry, but I also permute the leg 1 and leg 2. And this graph should be antisymmetric in leg 1 and leg 2. Then we also have a U channel, which is 1-3 channel here, which is adjacent. So there has to be an NU. And let me draw that as a non-planar graph. It is planar in this ordering here, but just because I want to distinguish the graphs so they don't look exactly the same, I'm going to draw it as a non-planar graph. And then there's one more partial amplitude that you can write down, which looks different, and that's the 1, 4, 2, 3. And so this will have a 2-3 channel, which is what I call T channel here. So let me write down NT over T. It will also have a 2-4 or 1-3 channel, which is the U channel. So write down NU and this non-planar graph again over U. And again, so these signs here I can get by realizing that there are certain permutations I have to do which affects the trivalent vertices, and that introduces a minus sign here. I could have put a plus sign here, but then I have to put 2 minus signs somewhere else. So this is a more democratic way of doing it, where I have each partial amplitude has a minus sign and each of them has a plus sign. All right. So writing it like this, you can see that the U1 decoupling. So the U1 decoupling is just that the sum of these guys has to equal to 0. That's a U1. And you see it's manifest here. This one cancels against this one. This one cancels against that one. And this against that one. So it's just manifest. And you can repeat this exercise at higher multiplicity, 5 point, 6 point, and so on. And as long as you write out the diagrams and put the right signs in front of them, modulo some ambiguity in what you call your numerator, you're always going to find pairwise cancellation, and that's just going to implement your KK relations. So in this way of thinking about it, there's no mystery why the KK relations are there. It's just a consequence of having trivalent diagrams with antisymmetric vertices. All right. Oh, yeah, and yesterday somebody asked me, why is there no quartic diagrams? Obviously, if I consider Yang-Mills, I should have a quartic Feynman rule. You could introduce quartic diagrams here, but it turns out that they don't actually do anything interesting in this, this formal way of looking at it. And furthermore, we know that even the quartic diagrams will come with FABC, structure constants. And this decomposition here, which the color decomposition and so on, was effectively using trivalent diagrams alone coming from the FABC. And it turns out that the 4-point vertices, you could introduce them, but you can also absorb them into what I mean by these numerators here. Because obviously they won't have a pole, but I can artificially introduce a pole. I can take a contact diagram like this, and I can say that let's pretend that it has an S-pole, and then essentially just multiplying by S over S, and then this S goes into the numerator and S. So you can artificially promote your contact diagrams to cubic diagrams by just changing what you mean by your numerators. And that way you can get away with not using them. And it also makes sense from the point of view of gauge symmetry. So we know that the quartic vertices in Yang-Mills actually don't carry any additional physical information compared to the cubic one. The quartic ones are just there to make sure that whenever you do calculations, you get something gauge invariant at the end of the day. This also has to do with the fact that when you do BCFW recursion, you don't need to feed in the input of the quartic vertex. You can just start from the 3-point amplitude and compute any tree-level amplitude or loop-level amplitude in Yang-Mills. So the quartic one is just a redundant, just an artifact of redundant description of Feynman rules. All right, so so this n-2 factorial KK basis is, it is a true basis if you consider a generic theory with adjoint particles and single trace interactions and so on. But for Yang-Mills, it turns out not to be the correct basis. There's a smaller basis. So yeah, let me just complete there. So this is irreducible. It's irreducible in a general theory. But for many of the theories we love, there are smaller bases. Smaller. And so there's an additional set of relations, which we often call BCJ relations, which can bring down this basis by fixing one additional leg here, and then the basis become n minus 3 factorial. And so let me give you one of these relations. It's not going to be the complete set of relations. Well, the complete set of relations is going to be given by permutations of this one, but I only need to give one. And well, I'm going to start a bit funny by writing down something which is 0, but I think it adds a little bit of clarity. So again, just like we did for the Kleist-Coif relations, we're going to consider one leg and we're going to permute it. So let me denote that leg with a blue color. And then we're just going to pick the rest to be in the canonical order. So we're going to permute this one around. Let me write down the amplitude first and then write down the prefactor. So we passed it through leg 2. So then leg 1 ends up here. And then we have 3 up to n. And then there's a prefactor here. And the prefactor is going to be momentum P1 times all the momentum before leg 1. So we can also include leg 1 for additional clarity. So that's just going to be the sum P1, P2. So that's just the sum P1 plus P2. And so we just keep doing that. So that's going to be P1 dot P1, 2, 3. A, 2, 3, 1 to n. And then, well, just add more. And then the last term is going to be P1 dot P1, 2, 3, 4 up to n minus 1. Well, if I sum over all of them, I get 0. So let me pick this one to be the last one. A, 2, 3, 1, and n. So this sum here is 0. So it looks a little bit like the Kleist-Coif relations, but instead of having prefactors which were integers, which were plus minus 1, now we have momentum-dependent prefactors. So if you don't, maybe you can consider that I don't care about such relations, I just care about the simpler relations which has integers as coefficients. Well, then the Kleist-Coif relation is the basis. But if you allow coefficients which are momentum-dependent, but don't depend on the particle content, the spinors or the helicity or the polarizations, then there are such relations like this in Yang-Mills. So let me actually indicate this by saying this is Yang-Mills now. It's not true in your generic random theory, but for certain nice enough theories, this identity is there. Now, this relation looks maybe suggestive. Maybe it looks like something. Well, almost looks like a word identity of the type we saw in Shruti's talk. And there are some deeper understanding of it, but let me just tell you the original understanding, which was in the work we did more than 10 years ago. So the non-trivial claim here, I made a mess, can I try it up? Yeah, so the non-trivial claim so the BCA relations come from what we call color-kinematics duality. And so that's the topic of the first lecture. So I finally got to the topic of the first lecture. And so what is color-kinematics duality? Well, it is for every Jacobi identity that we had for the color factors, which I can write as some set of three-term identities. So every such set of three-term identities that you can write for the color factor, you should impose a kinematic Jacobi identity. For the numerators. And we can already see here that I was sort of mimicking how the color factors and the numerator behaves under permutations. Now that's not a very severe constraint. You can basically say that you can always impose on any theory, because that just follows from Bose symmetry, that the product has to be even under flip. So clearly, if there's a minus sign in the color factor, you have to have a minus sign in the numerator. But the more non-trivial part is that also the other type of relations that the color factors satisfy, which is the three-term identities, can also be imposed on the numerators. And I can also draw this diagrammatically. I think I did it last time, but let me do it again. So each Jacobi triplet corresponds to 3 diagrams. And so let me draw it like this. And if I draw it graphically, I like to put in a minus sign here, otherwise I get confused. And so maybe if I want to be slightly more precise, there could be a potential minus sign here, depending on how you have labeled your graphs, right? So that's just a choice that you have to label your graphs, so there might be potential minus signs here. But graphically, if I define a certain ordering, 1, 2, 3, 4, and maintain that ordering, the identity should look like this. And this is now not a 4-point identity, because this could be embedded in some larger graphs. So maybe I should put some, a blob here, indicating that there could be many legs hidden here. So this is a graph identity at endpoints where you might have many legs, and so on. So you pick a subgraph, 4-point subgraph, and you do this this three-term move or Jacobi identity, and you set it equal to 0. And you do it for all such triplets. You solve for it. You can check that that will give you such relations. I think actually my plan is to not illustrate the full details of this, but maybe instead give a homework exercise at 4-point, where you can confirm what I'm saying is correct. Maybe that's the wrong direction. Let me just move it all the way up. All right, so I'm just going to give you a simple homework example. So show that at 4-point, you can write your relations between amplitudes and numerator in this following equation here. So let's take 2 of the orderings. We know that there's a 2-dimensional basis of in the Kleist-Coif basis. So let's pick 2 of them. We're going to pick this ordering. We're going to pick 1, 3, 2, 4. So that's my standard Kleist-Coif basis, keeping leg 4 fixed and just permuting the 2 guys in the middle. And then I can write down a matrix equation where I have solved for my numerators, which I have up there, NS, NT, and U. So I solve for 2 of them. And so I write them here, NS, and then U. And then I know that my partial amplitude is a linear combination of these numerators. It's essentially what I have up there, except that you have to use a 3-term identity now. And the 3-term identity that I'm going to use is going to be NS plus NT plus NU equals to 0. So in my labeling scheme that I have up there, this is all going to be plus. Right, so the homework exercise is to write down what this matrix is. And you can figure it out from up there. I'm going to give you the answer, so all you have to do is confirm it. So it's going to be 1 over S plus 1 over T. And the entry over here is minus 1 over T. This is 1 over T. And the entry here is minus 1 over T minus 1 over U. And I hope I got it right. If I didn't, let me know. So the first part of the homework exercise showed that you can write your partial amplitude as this matrix equation, where this is a 2x2 matrix. And we can also introduce some notation. Well, we already introduced some notation for this guy. This is basically A1 sigma 4, right? Let's introduce a notation for this guy. Well, I can just use the same notation, so let's call it N1 comma sigma comma 4. Because obviously, when I did the color decomposition, I was using Jacobi identities for color factor, and so I had color factors labeled like this. So it's probably a good idea to use the same labeling for my numerator factors, since they satisfy the same Jacobi identity. Okay, so then for this guy, I'm just going to call this the matrix M, which depends on the permutation sigma. Sorry, let me, I guess I should call this maybe rho. Let me call it rho. So this depends on sigma and rho, which is the permutation over here. So this is basically a matrix equation that looks like this. This object here is the sum over permutations rho, where these are the entries of this matrix. Yeah, and let me also clarify what precisely this is in terms of graphs. So 1 row 4 is my half-ladder graph that I said was a good basis for the color factors, and since we're treating color factors in the same way as kinematic factors, I might also use it as a good basis for my kinematic factors. Sorry. Let me call this sigma. Okay, so first homework, check that this is the correct matrix, compatible with what I have said up there. The next part is confirm that this matrix is degenerate. So this is a degenerate matrix, meaning that its determinant is 0. Now, since this determinant is 0, it means that its rows and columns are not independent. So in particular, these two guys are not independent, right? So this implies that there's a relation, which is that S times this partial amplitude, 1, 2, 3, 4, is equal to U A 1, 3, 2, 4. And that is, this is the 4-point BCA relation, which I should say many people point out that this has been known for a long time, which is probably true, but it's part of a general family of relations which were only discovered, what was it, 14 years ago now? Anyhow, and there's many relations which are more complicated than this one, but they can actually be obtained from permutations of this simpler relation and substituting it back and putting it in a basis, right? So this is not yet reduced to a basis like we did for the Kleist-Korf relation, but it is a sufficient set of relations by considering all the permutations. All right. And then, well, so this is how it works at 4-point. And, well, I shouldn't give you homework to do it at endpoints, but I can just say the answer. So at multiplicity n, yeah, and now I have to apologize. I think I already apologized yesterday in advance, but this n and this n is different. Sometimes we call one of them capital N, but well, this is just the numerator, this is just the multiplicity. I hope it's clear from the context. So at multiplicity n, the Jacobi identity using the Jacobi identity to reduce the numerators will give you a matrix, and that matrix will be degenerate. So let me just write it again. I mean, it's exactly the same formula as I had over there. So the Jacobi identity gives you an n minus 2 basis. Well, sorry, that was already clear. So this is the color Jacobi. Of numerators. which is what I have here. That is my basis of numerators. And this is what people call, either in some older literature, this was called propagator matrix, because it's just a matrix of all the propagators that you can have. Or I think these days people prefer to call it the biadjoint. Scalar amplitude. And I mean, it's obviously some scalar propagators, so it turns out that it has an interpretation as some amplitude with two color orderings, and that's why it's called biadjoint. I will maybe discuss it next lecture a little bit. Yeah. Did I? Yeah, this is row. Thank you. And now the claim is that the rank here, the rank of this matrix M sigma rho is equal to n minus 3 factorial in Young-Mills and in many other theories. You know, maybe not your random theory that you constructed by throwing darts, but certainly in many theories. Yes, and this matrix by itself is n minus 2 factorial times n minus 2 factorial. So it has quite a lower rank than its actual size. Right, and the way to get there, well, the way to, well, that just shows that this matrix has a lot of redundancies, relations between its rows and its columns, and those relations between the rows are basically reflecting the relations between the amplitudes. So that gives the BCA relation. And you can check this case by case, and you know, it always gives rise to these kind of relations. All right. Now, let me say why we would actually should, well, let me say why we should have expected this. I mean, in hindsight, we should have expected it. So why is this matrix degenerate? M sigma rho degenerate. Well, one tentative answer, I mean, I'm not saying it's a proof, but so the problem is that if it wasn't degenerate, so if it were not, then you can invert this equation by just finding the inverse of the matrix and put it on the other side, and you can solve for the numerator. The numerators can be uniquely solved. in terms of gauge invariant amplitudes, partial amplitudes. And that's a problem because numerators of Feynman diagrams, if we interpret it like that, they should not be gauge invariant. Especially not if the numerators are local, which is something you would get from a Lagrangian. There's no way they should be gauge invariant, right? So if you have local numerators and you can make them satisfy the Jacobi relations, and it's a gauge theory, you know that this matrix has to be degenerate. Otherwise, there's a contradiction in having non-gauge invariant numerators, like non-gauge invariant Feynman diagrams. Now, there's some exceptions to this, and the exceptions happens, for example, when you can't find local numerators, but you might find non-local numerators. There could be exceptions when you're not really looking at gauge theory. Maybe you're looking at a theory which has matter only, and so on. This argument could fail, but I think in general it's a pretty good argument. We should suspect that this is a fairly general property. It doesn't really tell you what the rank is, but it's kind of telling you that the rank should be not saturated. And so there are some new relations you would expect. How am I doing on time? Yeah, there's a question? Here. There. Yeah, so here, of course, I did not use color-kinematics duality yet. I just showed you that the Kleist-Coif relations are manifest in this way of writing it. But then, since I had three numerators, ns, nt, and u, I need to reduce the number of numerators to get to this equation, right? So that's where I used the Jacobi relation. So I used that identity that ns plus nt plus nu is 0. That's how I can write it in a two-dimensional basis, right? Yeah, so first you put your color factors in a basis to get your partial amplitudes. Then you put your numerator factors in a basis, and you can pick it to be the same basis. That way you get a symmetric matrix. So my matrix is, well, it's almost symmetric. There's a minus sign, but yeah, there's some minus signs floating around, unfortunately. But yeah, so you can do the same reductions for the numerator as the color factors, and then you go down to the n-2 factorial basis, and then you get the matrix, which is a square matrix. You can ask the question whether this is full rank or not, right? If it's full rank, you can invert it. That means that you have gauge invariant numerators, which you might have. For example, if you consider a scalar theory, like the one that we typically call the bi-adjoint scalar theory, its diagrams are gauge invariant. So you can have gauge invariant numerators, but in a true gauge theory where you have gluons, you should not expect gauge invariance. You should expect some degenerate matrix. All right, yeah, I'm not sure if I answered your question. Yeah, okay, maybe. Yeah. Yeah. Mm-hmm. Yeah. You ask, why do I have 3 numerators rather than 6? Because in principle, you can think of this 6 diagrams as being different diagrams. Is that what you're asking, or no? Yeah. 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 Yep. For the amplitude, well, the partial amplitude is a rational function, and of course you could put them on a common denominator, but that's usually not well. That's usually not a good idea unless you're using spin helicity. Maybe then you could write things in terms of the Park-Taylor factor. But I think in general, it's a bad idea to put things on a common denominator. I mean, if actually you're obscuring the fact that there is no well, you're obscuring the fact that things can be written in terms of diagrams that factorize in the proper way. I mean, yeah. So, yeah, I'm not exactly sure what you're asking for. But yeah, generally we don't consider the numerator of partial amplitude. We consider the numerator of a diagram because we know that on top of Feynman diagrams there's some numerator which has to do with the locality properties of the theory. You expect that to be a polynomial, and that's how you know that you're talking about a local quantum field theory. All right, there was another question here. Yeah. 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 So they're not unique. Yeah. Well, if you pick a gauge, I mean, is it gauge invariant, or I mean, you were saying pick a gauge and it's accidental that there might be gauge invariant in that gauge? Is that, well, yeah. Yeah, you have to choose a gauge, and yeah, you'll get different. I mean, imagine you had a Lagrangian which computed its numerators. You could pick a gauge for that Lagrangian, and you would get different numerators, right? So this ambiguity in what the numerators mean is just a reflection of the inherent gauge freedom in the gauge theory. Now you're saying there might be some very special gauge choice, which is true. I mean, in fact, this relation, the three-term identity that we're imposing, is a restriction of what gauges you're allowed to have. But nevertheless, it turns out that restriction is not sufficient to actually pinpoint a unique gauge. And I think if you add some additional constraints at 4 point, you can get unique numerators, but at n points, again, you will start having non-uniqueness, right? So, yeah. All right. All right. So let me move on. I guess I'm kind of running out of time. I guess I was supposed to talk about gauge invariance next, but maybe let me skip ahead a little bit and talk about the double copy. But okay, before that, I need to write my amplitude again. So let me write my full amplitude now. So now I'm going to reassemble it with color factors. So the claim is that now I can write my amplitude as before. It was a sum over cubic diagram. Now it's all of them, so all of the cubic graphs. I, Ci, Ni over Di, right? So last lecture we called Ni over Di. We called that some kinematic partial amplitude, or well, it's not really a partial amplitude, but it's some kinematic coefficient. But now we're just going to write it as ni over di, summing over all cubic graphs, which is basically going from 1 to 2n minus 5 factorial, double factorial. That is all the cubic graphs. And so now we have exposed that there, we can treat the color factors and the numerators very symmetrically. They satisfy the same relations. They're on equal footing, at least algebraically. And writing like this suggests that there might exist other amplitudes that you can write down, which has a similar form. So this is what we call the double copy. So what we're going to do is we're going to take this color factor here, and we're going to replace it by another copy of numerators. Just to distinguish it from that copy, let's put a tilde on it. And then we get an amplitude, let's call it m, which is the same sum. I goes from 1 to 2n minus 5 double factorial, but now is ni triddle over di. Right, so this is just something we can do. Well, it's not clear that we can do it, but it's very suggestive. We have two objects that behave exactly the same way, at least algebraically at the abstract level. I mean, there might be additional constraints, but for the Jacobi identities and the antisymmetry properties, they behave the same. So let's just introduce a second copy of numerators and write up this amplitude. This amplitude should have very similar properties to this gauge theory amplitude. Let me just be more specific. Let's call it Yang-Mills. So the question is, what is this amplitude? And I think it's fair to call it amplitude. It's going to have very nice, it's going to have the same poles as that amplitude. It's going to have manifest factorization. Recall that the numerator here will factorize into smaller pieces, just as was described by Jaroslav in this morning. And so the fact that this is a product, it will still factorize in the same way. So this will have a lot of properties of an amplitude. But what additional properties will this have? So the additional properties that this has, first of all, if this is a gauge theory, which it is in Yang-Mills, we will have polarization vector. This will be a function of polarization vectors. Here we'll have two copies of polarization vectors. So we will have spin 2 polarizations. Epsilon mu nu, which I can just identify as epsilon mu times epsilon nu. In general, maybe I should have put a tilde on top of my second set of polarization vectors like I did for the numerator. But for now, let's just keep them the same. Furthermore, I can say that the dot product of them is 0. That just means that they're null vectors. And if that's the case, that means that this object here is symmetric, manifestly. It's also traceless. And it's also transverse, because these are polarization vectors that depend on momenta. So, well, if you know anything about spin 2 states, you should know that on shell they should be traceless, transverse, and symmetric. And so that's the true degrees of freedom of a spin 2 state. Second property is that if this was Yang-Mills, we know that Yang-Mills has graphs which has a one derivative interaction, like the Feynman rule, the cubic Feynman rule has one derivative. And if we're squaring the numerator which carries these derivatives, we should expect something which has we should expect something which has two derivative interaction, right? So this is two derivative in each vertex, right? So this is a two derivative cubic interaction. And I say cubic here because we're using cubic diagrams. You can check what happens if these cubic diagrams collapse to a contact diagram. It turns out that contact diagram will still be two derivative. So in fact, all the contact diagrams that are generated by the double copy here will be two derivative. And the third property, which is less obvious, is that this amplitude here has diffeomorphism symmetry. Whoops. Whoops. So the on-shell version of diffeomorph symmetry, or linearized diffeomorph symmetry, is just that we've replaced this polarization tensor. Well, we can keep itself, but we add a small perturbation, and the perturbation is the momentum of this polarization, p mu, and then we can have an additional vectorial polarization, which I'm just going to write like this, and then we symmetrize it. If an amplitude is invariant under this replacement, it has on-shell diffeomorphism or linearized diffeomorphism, which is sufficient. Generally, that's a sufficient argument why the whole theory that you have coming from this, well, the whole, like if you have a whole S matrix which is invariant under such replacement, you would expect that the underlying theory has full nonlinear diffeomorphism symmetry. So let me try to sketch why the double copy will have this invariance. I had a very long derivation here, but I think it's way too long. But we can first consider what happens when we do a gauge variation on the Yang-Mills amplitude, which we can do. We can just take some amplitude written in terms of polarizations. So we pick some polarization, epsilon p, and then we replace it by p mu. Let me also keep the original epsilon around for such that it becomes an invariance condition. Yeah, so we perturb the polarization with its momenta, and we expect the amplitude to be the same, right? And so of course, if you do that on this representation, what will happen is that you will modify what you mean by your numerator, right? Color factor does not depend on momentum, does not depend on polarization. The only thing that depends on polarization is n. So this implies that my numerator ni, or the set of numerators ni, could possibly pick up a shift. Let me just call the shift delta I. And this shift here is simply plugging in p into my numerator instead of epsilon. So this is my definition of what delta is here, right? So if you do that in this representation, and you want the Yang-Mills amplitude to be gauge invariant, which obviously you want, otherwise you have done something wrong when you computed it, you should expect that you have a formula that looks like this. The sum over all graphs, ci delta I over di, has to be equal to 0, right? If this is true, then the amplitude in this representation will be gauge invariant, right? So this could be true if the delta i's are 0, but as I already argued, the numerators are not gauge invariant, so they must pick up a shift when you shift the polarization. So we definitely know that delta i's are not 0. So the only way that this can be 0 is if there are some relations between the color factors, which we know that there are. There are relations between the color factors. These are the Jacobi relations, right? So this is 0 because of Jacobi identity. So Jacobi identity makes this 0. And maybe it sounds like I'm trying to argue that it's true. No, I'm assuming it's true, because otherwise this is not an amplitude, right? So we take this to be true from the start, so we take it true by definition. And if this is true, we can then derive that the double copy is invariant under this more general replacement. And the reason why it's true is that because now, if we take the double copy and replace epsilon mu nu by epsilon mu nu plus p mu epsilon nu symmetrized, what you will get is that, well, you will get something proportional to that. So that's going to be m itself. Then you're going to get sum I ni delta I over di plus sum n I triddle. Let me put a triddle. And well, I guess I have to put a twiddle here, because that could also be, you know, what you get from doing a gauge transformation on n triddle. You can take them to be the same. Then you would just get a factor of 2. Yeah, if n and n triddle is the same and delta twiddle is the same, it just becomes a factor 2 there. Now, we know that this is 0. This is equal to 0 because of Jacobi identity. And it's true by default, because the Jacobi identity that this guy satisfies, I have assumed that this guy satisfied as well. So algebraically, it's actually the same equation. And likewise, this is equal to 0 by the Jacobi identity, because this is also, by default, the same equation, assuming that this n triddle satisfy the same Jacobi relations as the C's. Yes. So this shows that the linearized diffeomorphisms will leave the amplitude invariant, and since this was true for essentially all the tree-level amplitudes, it shows that this gives something which is diffeomorph invariant, at least at the tree level, as long as this argument, for this argument. You can generalize this argument also to the loop level. I think that was the last thing I was going to talk about today, but I'm not sure if I'm going to have too much time to say anything about loops. Maybe I just ask, is there any question on this particular thing here? Yeah.
Well, we have to go for a lunch. Because
you want me to finish? Let me just say one more thing, and then maybe we can have questions. So this double copy here, I didn't really say where n and n tilde come from. Well, n here comes from Yang-Mills, and tilde can come from somewhere else. So in general, we will have a map. Let me just write it here. We have a double copy map. Where we have two set of amplitudes, sum I ni ci over di. So we have a pair of amplitudes Ni triddle, and now let me also put a triddle on the color factor. It doesn't really matter. The color factor could be different as long as the Jacobi relations are the same, which they have to be if this comes from a Lie algebra. So we have a pair. We have a pair of amplitudes, and the map is simply to just strip off the color factors and write down the product of the enumerators. Right, this is my map. And now it's kind of obvious that this could be two different series. So in fact, this map at the level of amplitudes will be a corresponding map at the level of series. So if you have a gauge theory, and we can denote it as a tensor product, a pair of things is just a tensor product. So this is a different gauge theory triddle, and a map to a gravitational theory. Maybe I forgot to say that the whole punchline of diffeomorphism is that this is a gravity. So let me just replace my question mark. And so in the case of Yang-Mills, we can call this GR. It's not quite GR because there's also additional states, but at least at tree level, the map is between Yang-Mills and GR. And in general, it could be more complicated, especially at loop level. But you can also do different series. Maybe one of them is not Yang-Mills. You get something different. Anyhow, I think that's all I'm going to say today.
I cut the question because I promise we won't be later than yesterday, which would be. But please come here and ask Henrik directly, and there will be still a lecture tomorrow. And it is not before the lunch tomorrow, no?
Yes.
So it's good.
So I will abuse that
so thank you,
tomorrow.
Henrik, and sorry.
Yeah.